Well, this is where I discovered fluid dynamics as a subject in science. I came here in 1953. I just got my degree in engineering, and I had by then already made up my mind that I would like to do aeronautics if possible. Somewhere around 1950, more than 60 years ago, I came here as a young kid to this very quadrangle. And what I saw was the Second World War Spitfire parked under this tree. It was an open day at the institute, and there were thousands of kids all over the place, and I was one of them. And that was the first time I encountered an aircraft, so I could go touch it. The Spitfire had made a big name for itself in the war. So I saw that and I said, okay, if there's some engineering I'm going to do, that's what I should do. I came here, and when I came here as a student, there was that wind tunnel at the back, that round thing that you see, driven actually by an aircraft engine from the same kind of Spitfire. And all of the department was only in that building. The office was there on top of the wind tunnel. And there was a lecture hall here and some labs at the back. So in 1953, when I came here, the head of the department was a well-known German scientist, Professor Tietjens, who had come from the Center of Fluid Dynamics Research in the world, which at that time was in Germany, Göttingen. And he was the one who first started a course on fluid mechanics, which made the subject attractive to me. He left in 1955. And at that time, after I'd done my diploma here, as it was called at that time, it was like a master's in engineering degree, I had two options before me. Either I would continue research in fluid dynamics, or I said I joined the meteorological department. I was already in that, at that time, interested in things connected with weather and climate and so on. So Professor Dhawan, who at that time was a young assistant professor in this department, had been busy building labs. There was a high-speed lab there, there was a low-speed lab here and so on. And I'd actually done work with him during those 2 years. And he said in 1955, why don't you come and join us for research here? So I was very happy he asked me that, and I said, a very enthusiastic yes, and spent 2 more years here doing research. After 2 years doing research in the aero department, I went away to the United States and came back just before New Year 1963. By then, Professor Dhawan had become the director of the institute. And during the following years, I used to discuss a great deal what I was going to do in the aero department. But slowly the idea grew that the most important fluid dynamical problem facing the country was actually the monsoons. And I went and argued with Professor Dhawan that it was very interesting that in India, the big centers of research were not doing anything in meteorology, although that was one of the major problems facing the country. So around the 1970s, Professor Dhawan finally bought this argument. And he said, all right, we will appoint one person on the faculty to see how it goes, provided you or somebody will take responsibility to look after his interests. I said, yes, I'll be happy to do that. And that was how Dr. Shankar Rao was appointed as a meteorologist on the faculty of the Department of Aeronautical Engineering. Then in 1972, part of the big transformation that Professor Dhawan had undertaken on this campus, the Center for Theoretical Studies was set up. And that is where the center began, in this building, which, when I came here as a student, was actually the Gymkhana. And I remember playing ping pong in that building. And these were tennis courts. It was symbolic of the change that had come over the campus when Professor Dhawan took over. Science and research came back to center stage. The Gymkhana moved on the other side of the road. In 1973, among the very first appointments to be made was that of Professor Sulochana Gadgil, who came here with Professor Madhav Gadgil. Both of them joined the Center for Theoretical Studies. Sulochana Gadgil was a mathematician, but she was very interested in problems in the atmosphere and the oceans. And her advent on the campus gave greater fillip to the budding research program in atmospheric sciences. And now we were 3 people here, greatly interested in atmospheric sciences. Well, in the next several years, there were more people in the institute who had an interest in atmospheric sciences. And by the end of the 70s, we had a thriving interdepartmental group. And that included people like Dr. C.R. Prasad from mechanical engineering, who was an expert on use of lasers and was very interested in using them in atmospheric measurements. Professor Devanathan, Mrs. Devanathan at the Department of Mathematics, who did fluid dynamics and was very interested once again in atmospheric problems. Professor Prabhu at the Department of Aeronautical Engineering. Professor Narayana Iyengar at the Department of Civil Engineering. Professor J. Srinivasan joined us, came from IIT Kanpur, the background in atmospheric radiation. So it was beginning to be a thriving group. And therefore the idea came up that it was time to have an identity of our own. And so at first we made proposals for the establishment of a Center for Geophysical Fluid Dynamics. But by then, this idea that we needed other centers of research in atmospheric sciences, in meteorology, was beginning to spread in the country. There was a committee headed by Dr. Ramana, which looked into the organization of meteorology in the country. And I happened to be a member, because by then, they were already seeing that there was some interest in the Institute of Science. And among the many recommendations we made was one which said we should set up at least 2 centers of atmospheric research in the country. Maybe one in Delhi, one in Bangalore. This recommendation was accepted by the government. And I think Professor James Lytle, a very well-known fluid dynamicist, who himself had interest in a wide variety of problems in fluid dynamics, which included the atmosphere and the oceans. He came here on a visit, came to India, came to Bangalore here, and looked at the work which was going on. And he wrote a strong letter to the government, saying you should set it up. I see now that there's a lot of work going on in these places. So that's how, in 1982, the Center of Atmospheric Science got to be approved. The Center for Atmospheric Sciences, when it was established, started a new branch of science in this campus. There was never any formal atmospheric research done in this campus before then. But that doesn't mean that there has been no earlier connection between the Institute of Science and meteorology. One of the strongest connections was that several students of Sir C.V. Raman, physicists basically, and I'm sitting right next to C.V. Raman's table here. Several of his distinguished students went on to do meteorology. They joined the India Met Department and made very significant contributions. Perhaps the most notable among them is K.R. Ramanathan, who worked with C.V. Raman in his Calcutta days, and then went on, after he joined the Met Department, to become a pioneer in the measurement of ozone in the atmosphere in the country. He also made this very interesting discovery that the coldest air in the atmosphere was actually a ring around the equator, not the poles, it's the equator. Then there was Ramdas, who was a pioneer in agricultural meteorology, not only in India but in the world. Dr. Pisharoti, whom I had a chance to know very well. I got to know both Professor Ramanathan and Professor Pisharoti quite well in later years. Pisharoti was the spirit behind the Indian Institute of Tropical Meteorology in Pune. So there were several of these connections through students who worked here with C.V. Raman. An earlier and more indirect connection was Sir Gilbert Walker, a very distinguished British scientist who came here to head the Met Department. And the methods that he introduced, statistical methods that he introduced, are still used in the Met Department. The basic principles, not the precise formulas he made, but the basic principles are still used for long-range prediction in India. He was also the discoverer of what's now very famous as the El Nino Southern Oscillation phenomenon, although those names were not used at that time. But he saw the connection between the monsoons and the Pacific. So that big circulation which is responsible for this connection is now named the Walker cell in his honor. So there were all these indirect connections. But the CAOS signaled the formal recognition by the institute. This was a very important subject and a very interesting one. Well, from one point of view, the idea about a Center for Atmospheric Sciences or something like that began to crystallize around 1969, actually. Because in 1969, the institute had a review committee headed by Professor Seshadri. And this asked for proposals from various faculty members about what should be done in the future. I and a very good friend of mine, Professor B.S. Ramakrishna, a very highly regarded academic from the Department of Electrical Communication Engineering. We were great friends and we used to talk about all of this. Professor Ramakrishna had not only been doing communication as electrical engineers understand it, but he was also interested in music, drums, strings, and so on. He did a very interesting experiment on the vibration of strings. It seems like an old problem, but it's not, in terms of what happens if the string operates at swings with large amplitudes. So I did some work with him, inspired by what he had done and so on. It slowly began to appear to me that there were very many problems in mechanics that were actually connected, although they were in different disciplines. And the institute already had a good group in mechanics in different departments. So we actually submitted a proposal to the Seshadri committee on what we called at that time coordinated mechanics. And at that time, also these discussions took place about the atmospheric sciences and so on. In 1975, we organized a workshop on geophysical fluid dynamics. Our earliest idea was that this center should be in the subject of geophysical fluid dynamics. Even there, the reason for choosing that word was that we realized that the atmosphere and the oceans were coupled together. They were no longer independent systems. You can't do atmosphere without knowing and doing something about the oceans. Sea surface temperatures and winds over the sea affect what happens on the continents too. We all know that the monsoon blows over the Arabian Sea. So we always thought of this at that time as a program in geophysical fluid dynamics. So in 1975, we held a workshop on geophysical fluid dynamics, this group, jointly with the Indian Institute of Tropical Meteorology. And one of the things that came up there was the desirability of doing an experiment on the atmospheric boundary layer in India. Now, I and my colleagues and students at the Department of Aerospace Engineering had been doing a lot of work on turbulence, had developed instrumentation, and made measurements, usually in situations which were relevant to aeronautical technology. But many of those tools and ideas could in fact be taken over or used to understand the atmospheric boundary layer. So the net result was that in 1979, we actually made a proposal to the Indian monsoon expedition, MONEX it was called. So this proposal was approved, and we set up an atmospheric boundary layer experiment in Balasore on the east coast of India. We selected Balasore because that was the place where there's the highest frequency of cyclones crossing the coast, Balasore in northern Orissa. We also had there a station run by Defence, an old station going back to almost East India Company days, where they were using it for ballistic tests. And we said we would set this experiment up, and it was approved. and we went to Balasore. We spent nearly 2 months in Balasore. That was a very interesting experience. I brought together people once again from many different departments in the Institute of Science. And it enabled us to see how whatever skills we had and were making flow measurements in the lab could be transferred to the atmosphere. Well, the atmosphere is not the same as the lab. In the lab, everything can be controlled. And if something doesn't work, you fix it and continue with the experiment. You can't do that in the atmosphere. It happens only once. And we realized that it was actually much more difficult to do it in the atmosphere. But Professor Prabhu and our other colleagues did a wonderful job. And at the end of the experiment, after 2 months, we began to see that this was something which we could do. And some interesting results emerged as well. We measured the fluxes and so on. But I think the most important outcome of MONEX, as far as the program at the Institute was concerned, was that we realized that we could formulate and run our own field experiments. This is something which the Institute had never done before. And we realized that there was a pool of skills in the Institute which could actually design new instruments and make them operate. It turned out that the apparatus that was made, very largely by Professor Prabhu in the aeronautics department, was actually very advanced for its times. It was already a computer-controlled surface observation tower. And as far as I can see, first one ever in the world. I know that because 50 miles up the coast, there was an American team making also measurements of the same kind, probing the first kilometer above the surface, which was also our objective. And the Americans brought their own equipment from the United States, and we had equipment very largely made here. So our equipment was homemade, and their equipment was industry standard. So we exchanged visits. Now their equipment was, calibrated, standardized, made by industry, and sleek. Our equipment was homemade, fixed here, but it had something which they didn't have, namely, this was run by computers already. Now, that came as a surprise to them because this was not run by computers as ours was. And that has something to do with the microprocessor revolution that was beginning to take place in India at that time. We were, in fact, the first customers to a microprocessor company which was established in Bangalore. And the man who ran the company was very happy to have his first customer from the Indian Institute of Science. So we knew that we could make these experiments and so on. So next year there was an eclipse at Raichur, and we took our old equipment once again to Raichur, set it up there, and we got very interesting results. By this time, our equipment had matured. We had one long experience in Balasore, and the equipment was now working very well. And it went on like that. So that experiment made in 1979, it was an international experiment, was, I think, a landmark in India's study of the monsoons, because it followed a similar experiment which had been done only on the Indian Ocean a few years earlier. And it represented the first attempt to make a systematic study using the most recent facilities and equipment and instrumentation to look at the monsoons once again. So, by 1980, we also had all these other people who had joined us, and their research programs were flourishing. Professor Gadgil and Dr. Sikka had discovered these cloud zones, which go across the country. Professor Gadgil, with Dr. Sikka at IITM Pune, started looking at satellite pictures of clouds over India. And this was one of the first instances of deep insights that were derived into the structure of the monsoons and the dynamics from the vantage point exploiting the ability of satellites to take a very wide global look. What they found was that during much of the monsoons, there is a broad band of clouds which really moves from the southern tip of India all the way to the Himalayas. Professor Gadgir gave a lecture on this subject here in 1980, which I remember very well. And here is what she found. This is one of the satellite pictures that was analyzed by her. This is born near Kerala, south of Kerala, and then travels all the way up to the Himalayas. It takes about 30 to 40 days to do that. So as it hits the Himalayas, it slowly dissipates itself. It's born once again. Another band is born, reborn at the tip of South India, and then starts all over again. So the monsoons now begin to appear as a sequence of migrations, propagations of cloud bands from the south to the north in approximately 30 to 40 day period. So they do that 3 to 4 times during the monsoons. This was a completely new insight into the dynamics of the monsoon, and it has changed the way that we look at variations in the monsoons. Monsoon variability is a major problem. When we get rain, in what parts of the country, in what sequence, all of these fall into place when you think of these northward migrations of what's been called the tropical or intertropical convergence zone for this cloud band. I think that was a major insight into the dynamics of the monsoons. The Center for Atmospheric Sciences was started on the 23rd of September in 1982, formally on this campus. It took another 7 years, 1989, before there was a building which could house all the faculty and students that were working on atmospheric sciences on the campus. In 1989, this building was open, but it housed at that time both the Center for Atmospheric Sciences and the Center for Ecological Sciences. Well, as the activities in the center grew, the Center for Atmospheric Sciences outgrew this building as well. And so in 1994, 5 years after it had first occupied this building, we moved out to the other building, which is now exclusively meant for the Center for Atmospheric and now Oceanic Sciences. So in 1994, it was still the Center for Atmospheric Sciences. 2 years later, in 1996, the center amended its name and became the Center for Atmospheric and Oceanic Sciences. So I call this the return of the oceans, because when we first made the proposal, it was actually for a Center for Geophysical Fluid Mechanics, which included the oceans and the atmosphere. So that was in 1980. So you can say that 16 years later, the ocean score came back to the concept that we originally had. And that's what it remains now. But it now also houses the Divecha Climate Research Center. Over the years, the center now has actually developed. There have been many more faculty members. And the program at CAOS is now very diverse, very comprehensive. Many aspects of the oceans and the atmosphere, large-scale circulations, weather prediction models, coupled ocean-atmosphere models. That's why it had to be the Center for Atmospheric and Oceanic Sciences. The oceans exert a dominant role in the Indian monsoon. And the discovery of a variety of parameters in the oceans that influence the monsoon. For example, the Indian Ocean Dipole and what's been called the Indian Equatorial Indian Ocean Oscillation. These phenomena, discovered by work done here in this center, are once again affecting the way that we look at the monsoons in deep and fundamental ways. There's been a great deal of research on the variation of the monsoons from year to year and from within a season in each year. These matters are of great concern to the Indian population And that study here has also been very illuminating over the years. I think that today, a combination of many different approaches followed at this institute. Field experiments in the Arabian Sea, the Bay of Bengal, leading role played in the formulation of the Indian Climate Research Program, the leading role that the center has played in the formulation of the concept of the satellite megatropic, probably to be launched in September, an Indo-French satellite which looks at convection in the tropics, the global tropics. And then a very effective program of interaction with agriculturists about what scientists can do to help farming, the farmer. So it's a very wide range of programs. Let me tell you one example in which I have myself been involved, which is in simulating clouds. Clouds are a central issue in simulating monsoons. Our skill in predicting the monsoons will go up a great deal if we understand clouds better. Although clouds are such objects of common observation every day, we wonder at them even when we're kids, it may come as a surprise to most people that we don't understand the dynamics of clouds. And uncertainty about the effect of clouds dogs the prediction of the monsoons as well as climate change studies. So it would be of great value to be able to simulate cloud flows in the laboratory. Professor Bhatt and I here have had a program which goes back to the 1990s, so more than 20 years we've been looking at it. And here is one result from such an experiment. I have here a picture, clouds in nature on the left as they're observed, and cloud flows that we can produce in the laboratory. And you can see that there's a great resemblance in these clouds. I think it's for the first time that we are able to reproduce in the laboratory under controlled conditions in a repeatable way such a transient phenomenon as the clouds in the sky. And since these pictures were taken, we've gone even further, partly here and partly at the Jawaharlal Nehru Center for Advanced Scientific Research, where we now have a new setup. And we can reproduce a very large number of cloud shapes that we see in the sky, cloud forms, I would say, not the particular shape that we see in the sky in a laboratory flow. And this enables us to make controlled measurements in a way that is not easy to do in the atmosphere. And these are resolving problems connected with how much air the clouds suck in, what happens to the air sucked in from the outside as it's funneled up to these large cumulus towers, which have such a huge impact on tropical circulations. So if you look at the center today, the program is very diverse. The establishment of the Divecha Center for Climate Change Studies, that is another major step forward. Scientists in the center have always been interested in climate, but with the importance that climate change has assumed in the world as a whole, as a global phenomenon which requires urgent attention, center scientists have played a leading role. And the establishment of this new center is another recognition of the way that the scientists in the center have contributed to many different aspects of atmospheric and ocean sciences.